Something strange happened on Sunday night, and almost nobody on the news is connecting the two halves of the story correctly. At 21:52 Universal Time, a magnitude 6.9 earthquake struck beneath northern Chile, the largest South American quake in 17 months, on the same subduction system that produced the largest earthquake ever recorded by instruments. In the same minute, on the backside of the sun, where our forecasts could not see, a coronal mass ejection erupted from a dormant sunspot, throwing a solar radiation storm at Earth. The two events should be unrelated. The physics says they have to be unrelated. But this is the second time in 6 months that the timing has lined up to the minute. Stay with me, and by the end of this video, you will understand exactly what happened, why this earthquake was survivable, and what the synchronization actually tells us. Welcome to the Breakpoint. Let's get into it. At 21:52 Universal Time on Sunday, May the 25th, a magnitude 6.9 earthquake struck the rock beneath northern Chile. The United States Geological Survey assigned it the identifier US 6004S and placed the hypocenter 29 kilometers east-northeast of Calama in the Antofagasta region of the Atacama Desert. The depth was 109 kilometers. That depth is the most important number on the page, and we are going to come back to it, because the depth is the reason a quake of this size produced almost no damage in a populated region. It was the largest earthquake in South America in 17 months. It was the largest earthquake anywhere on Earth in 35 days, since the magnitude 7.5 off the coast of Iwate in northeastern Japan on April the 20th. It was felt across most of northern Chile, into southern Peru, and as far east as western Bolivia. The United States Geological Survey pager alert, which estimates fatalities and economic loss based on the magnitude, depth, and population exposed, came in green. 0 estimated fatalities. Under $1 million in damage. No collapsed buildings. No infrastructure failures. That outcome is not luck. It is geometry. And before we get to why this earthquake happened the way it did, there is another piece of the story that arrived in the same minute. A coronal mass ejection lifted off the backside of the sun at 21:50 Universal Time. 30 minutes later, a solar radiation storm began hitting Earth. The two events are not causally linked. The energy budget rules that out. But they happened in the same minute, and that is where the story gets stranger. A magnitude 6.9 releases the same total energy regardless of where in the Earth it happens. What changes is what gets to the surface. The vast majority of dangerous earthquakes happen in the upper 20 or 30 kilometers of the crust. The shaking from those events reaches the surface quickly, with very little attenuation through the rock above. A magnitude 6.9 15 kilometers down, beneath a populated city, is a building collapsing, fatality-producing event. At 109 kilometers down, that same energy travels through a much thicker column of rock before it reaches the surface. The high-frequency seismic waves, the ones that do the most damage to structures, are preferentially absorbed by that intervening rock. What arrives at the surface is a longer, slower, lower-frequency shaking, spread over a wider geographic area, but less intense at any given point. People in Calama felt it strongly. People in Lima and La Paz felt it. Almost nobody was hurt. This is the single most important thing to understand about today's earthquake. The pager green alert, the absence of collapsed buildings, the survivability of an event that on paper sounds catastrophic, all of it is a function of depth. The same earthquake at 15 kilometers under the same city would have been a different kind of headline. It is worth pausing on what 109 kilometers of depth actually means in terms of the rock the energy has to travel through. The crust beneath the Andes in this region is roughly 70 kilometers thick. Below that, the rock is mantle, denser, hotter, more plastic, and a very effective filter for the short wavelength, high-frequency energy that does the most damage to brittle structures at the surface. By the time the seismic waves arrive in Calama, the spectrum has been reshaped. The long-period waves, which buildings can ride out without failing, are dominant. The short-period waves, which crack concrete and snap rebar, have been heavily attenuated. This is the same reason why deep-focus earthquakes around the Pacific Rim, even at very large magnitudes, almost never produce the kinds of casualty figures that shallow events of equivalent size produce in similar populations. That is the headline result. The deeper physics result is the same. The May 25th event was a major release of stored elastic strain in the subducting Nazca plate, the kind of failure that happens only because the slab has been pulled, twisted, and stressed for tens of thousands of years before this minute. The release of that strain matters scientifically regardless of how it appeared at the surface. It tells us something about how the slab is behaving in real time. We will come back to that. Calama is a copper mining city of roughly 170,000 people, sitting on the eastern edge of the Atacama Desert at about 2,200 meters of elevation. The Chuquicamata mine, the largest open-pit copper mine in the world by excavated volume, is in the strong shaking radius. The ALMA Observatory, the International Millimeter Wavelength Radio Telescope at 5,000 meters elevation in the high desert further south, also lies within range. As of this morning, both facilities are reporting normal operations. The Peru-Chile Trench, where this earthquake occurred, is the system that produced the largest earthquake ever recorded by instruments, the May 22nd, 1960 Valdivia event, magnitude 9.5. The trench runs along the western coast of South America for roughly 7,000 kilometers, marking the line where the Nazca tectonic plate slides eastward beneath the South American plate at about 70 millimeters per year. That is one of the faster convergence rates anywhere on the planet. But the trench is not a straight line. Around the latitude of Arica, in extreme northern Chile, the trench makes a pronounced bend, concave toward the South American continent. The Calama epicenter sits on the southern flank of that bend, and the bends and subduction zones are not just curiosities of geography. They are zones of stress concentration, places where the plate cannot subduct uniformly, and the slab below kinks and twists as it goes down. The result is locked patches, anomalous earthquake populations, and a magnitude frequency distribution that differs from the straight parts of the same trench. If you have ever heard a seismologist talk about the Big Bend of the San Andreas Fault north of Los Angeles, that is the same kind of feature on a much smaller fault system. The Arica Bend is its giant cousin. What makes bends matter is that the slab below the surface cannot smoothly accommodate convergence around a curve. Imagine pulling a sheet of stiff paper across a corner of a table. The flat portions slide cleanly. The corner itself bunches, folds, or tears. A subducting plate behaves something like that, except it does it over hundreds of kilometers of vertical extent and tens of millions of years. The slab below the Arica Bend is twisted. Different parts of it are descending at different angles and different rates. The strain that builds up in those twisted regions is not released uniformly. It is released in clusters, sometimes as deep intraslab events like Sundays, sometimes as the largest megathrust ruptures the planet has ever produced. The 1960 Valdivia magnitude 9.5 rupture, in fact, propagated southward from a region not far from the Arica Bend, along a roughly 1,000-kilometer stretch of locked plate interface. Today's Calama event is on the same overall system. It is not a megathrust event. It is not the same kind of failure. But it is in the same neighborhood, geologically speaking, and the underlying stress that drove it comes from the same source, the steady eastward convergence of the Nazca plate beneath South America that has been going on for tens of millions of years and shows no sign of slowing down. The fault that slipped on Sunday night was not the megathrust interface, the boundary between the Nazca plate and the South American plate, where most of the famous Chilean earthquakes happen. It was a fault inside the downgoing slab itself, roughly 100 kilometers below the surface, where the slab is being pulled apart by its own weight as it sinks into the mantle. That mechanism has a name. It is called intraslab normal faulting. As the slab descends past about 70 kilometers of depth, it cools and densifies, and the heavier, deeper portions of the slab begin to pull on the shallower portions. The slab is in tension along its length. When that tension exceeds the strength of the rock, the slab fails, and the rock on one side of the fault drops down relative to the rock on the other side. That is normal faulting. It is mechanically the opposite of the thrust faulting that produces the great megathrust earthquakes on the same subduction system. Both kinds of earthquake happen on the same trench. They behave very differently. Megathrust events on the plate interface, like the 1960 Valdivia magnitude 9.5, can produce magnitude 9 catastrophes, devastating tsunamis, and shaking durations measured in minutes. Intraslab events like Sundays, tend to be deeper, smaller on average, and produce dramatically less damage per unit of magnitude. They are not insignificant, but they are a different problem from a public safety standpoint. 10 minutes after the earthquake, at 22:02 Universal Time, the NOAA Tsunami Warning Center issued a tsunami notification for the Pacific coastline. 10 minutes after that, the notification was canceled. To anyone watching the event unfold on social media, that issue and cancel sequence looked alarming. Some people read it as a mistake, some read it as a cover-up. Neither reading is correct. Here is what actually happened. Tsunami warning systems are automated for speed, because the warning has to outrun the wave. The first version of an alert fires on two pieces of information: the approximate magnitude and the approximate location. Both of those are available within a minute or two of the event. What is not available that quickly is the depth solution, and the focal mechanism, the calculations that tell you whether the earthquake was on the plate interface near the seafloor or 100 kilometers down inside the slab. If it is on the plate interface near the seafloor, the rupture can displace the water column and a tsunami is possible. If it is 100 kilometers down inside the slab, no tsunami is possible, because the slip is happening too far below the seafloor to push the water. The system issues the warning first and refines it later. Once the depth and mechanism came in for the Kalama event, the warning was withdrawn. The system did exactly what it was designed to do. It just happened in public. This is the part of automated hazard warning that almost never gets explained while it is happening. The decision to fire an early notification on partial information is a deliberate engineering choice. The cost of issuing a tsunami warning that turns out to be unnecessary is measured in inconvenience, an evacuation that did not need to happen, an hour of disrupted coastal activity. The cost of not issuing a warning for an event that does produce a tsunami is measured in lives. Coastal warning systems are calibrated to err on the side of the false positive every single time, because the false negative is catastrophic. The Kalama issue and cancel is what a well-tuned system looks like when it works. The fact that it generated a brief public panic is a communications problem, not a science problem. The both law statistical relationship, which is one of the more reliable empirical rules in seismology, says that the largest aftershock of a given earthquake tends to be about 1.2 magnitudes smaller than the main shock. For a magnitude 6.9, that puts the expected largest aftershock somewhere around magnitude 5.9. As of this morning, no aftershock at that magnitude had been recorded. That does not mean it is not coming. It means the 72-hour window in which most large aftershocks occur is still open. The other thing the window does is keep open, statistically, the very small possibility that today's event was not the main shock at all, but a foreshock to something larger. That probability is low. Most large earthquakes are not foreshocks to anything, but it is not zero. The standard seismological practice is to watch the 72 hours after a major event and see how the aftershock sequence develops before declaring the main shock the main shock. The clock on that window started at 21:52 Universal Time on Sunday. It runs out late Wednesday, Universal Time. That is the earthquake. Here's the other half of the same minute. At 21:50 Universal Time, give or take a minute, a coronal mass ejection lifted off the backside of the Sunday. The large angle and spectrometric coronagraph instrument aboard the Solar and Heliospheric Observatory captured the leading edge of the eruption in its C2 field of view at 22:12 Universal Time. Back calculating from the measured velocity gives a launch time of 21:50 to 21:52. The Mauna Loa K coronagraph, which observes closer to the sun than LASCO does, captured the shockwave structure and the plasma filament within 3 minutes of 2150. The source region was an old sunspot complex designated active region 4436. It had been on the Earth-facing disk earlier in May and had rotated past the sun's northwest limb roughly 24 to 36 hours before it erupted. From Earth's perspective, the source was no longer visible. The flare itself was occulted by the solar limb, meaning the GOES X-ray sensors that normally tell us when a flare is happening saw nothing. The forecast for the next 24 hours had called for quiet conditions, 15 numbered active regions on the Earth-facing disk, only a 50% probability of any class flare, no expectation of anything significant. The flare that produced the CME was on the backside of the sun and was not in the forecast at all, because the source region could not be seen. The CME itself was a partial halo, meaning it was visible expanding on one side of the occulting disk, but not the other. That geometry tells us it was not directed at Earth. The Type 2 radio emission that accompanied the eruption allowed an estimated plane of sky velocity of 650 kilometers per second, which is moderate. A faster CME, fully Earth-directed, would have produced a geomagnetic storm. This one did not. What it did produce was a solar radiation storm. At 0010 Universal Time on May the 26th, 30 minutes after the eruption, the NOAA Space Weather Prediction Center declared SON minor radiation storm conditions. The greater than 10 mega-electron-volt proton flux peaked at 23.79 particle flux units about an hour later. The greater than 100 mega-electron-volt channel, which measures the harder and faster particles, peaked at 0.57 particle flux units. The hard spectrum is the signature of an impulsive event particles, accelerated quickly and directly by the flare itself, not slowly by the CME shock further out in interplanetary space. The distinction between impulsive and gradual proton events matters because they tell us something about what happened at the Sunday. A gradual event, with a softer spectrum, comes from the shock driven out ahead of the CME, slowly accelerating particles over hours as it expands through the corona and the inner heliosphere. An impulsive event, with a harder spectrum like the one observed here, comes from the flare itself, the magnetic reconnection event that powers the eruption, accelerating particles directly in a matter of minutes. The fact that this storm peaked early and hard, with the higher energy channel populated relative to the lower energy channel, is the signature of a vigorous flare on the far side. We did not see the flare, because the disk it lived on was facing away from us. But the particles it threw at the inner solar system did not need a line of sight. They followed the local magnetic field, and a fraction of them found their way to Earth. The local time at Kalama, where the earthquake struck, is universal time -4. That puts the local time of the earthquake at 1752, within the same minute as civil sunset at the epicenter. The CME source on the sun was at the equivalent rotational position on the solar surface, just past the western limb relative to the Sun-Earth line. Both rotating bodies' active points were crossing past their local terminators in the same minute. There is no proposed physical mechanism that links those two facts. The coincidence is presented here as observational texture, not as a causal claim. This is not the first time something like this has happened in the recent record. On December the 6th, 2025, at approximately 2041 Universal Time, a magnitude 7.0 earthquake struck near the Hubbard Glacier in the St. Elias Mountains of southern Alaska. At approximately 2039 Universal Time, 2 minutes earlier, an Earth-directed solar flare peaked on the visible disk. That synchronization, within 2 minutes, is the most analogous prior event in the past 18 months. Today's Chile event is the second. 2 events are not a pattern. 2 events are not enough for any statistical inference. The question of whether solar activity can influence seismic activity is genuinely contested in the published literature. The most cited paper claiming a correlation is Marcatelli and colleagues on the correlation between solar activity and large earthquakes worldwide, published in Scientific Reports in 2020. That paper has been heavily criticized in follow-up work for selection bias and inadequate controls, and there is no consensus in the seismological community that the effect is real. The energy budget arguments make a direct causal link implausible at the basic physics level. The total kinetic energy of a typical solar wind perturbation arriving at Earth's magnetopause is many orders of magnitude smaller than the strain energy released by a magnitude 7 earthquake. There is no known mechanism by which a small energy input from above can release a large amount of stored energy below. That does not strictly rule out the possibility small triggers can release stored energy in nonlinear systems all the time, but it does mean that the bar for evidence is high, and 2 events in 6 months does not clear it. What 2 synchronizations do clear is the bar for continued observation. The Hubbard event happened. The Kalama event happened. They occurred within 2 minutes and within 1 minute of major solar events, respectively. That is enough to keep watching. It is not enough to say what is going on, if anything is going on at all. The 72-hour aftershock window for the Calama earthquake remains open through late Wednesday Universal Time. The expected magnitude 5.9 aftershock has not yet been recorded as of this morning. The very small statistical possibility that today's event was a foreshock rather than a main shock also remains open in that window. If a larger event were to occur, the United States Geological Survey, the Chilean National Seismological Center, and the international seismological community would have detection within seconds. The aftershock sequence will reveal itself on its own schedule. The zone radiation storm conditions are expected to decline over the next 12 to 24 hours as the proton flux falls back below the zone threshold. Operational impacts at this storm level are minor. Some increase in high-frequency radio propagation issues at high latitudes. A small additional dose for astronauts and crews on polar aviation routes, otherwise negligible. The Earth-facing solar disk remains in the forecast as quiet configuration. The 15 numbered active regions are still on the disk, and the flare probability for the next 24 hours remains low. What is worth watching is the next synchronization, if there is one. 2 events in 6 months is meaningless statistically. 3 or 4 in the same window would be a different conversation. The fact that the December Hubbard precedent existed at all is what makes today's Calama event worth noting in this particular way. If another large earthquake occurs in close temporal proximity to another major solar event in the next several months, that will be the moment at which the question of pattern stops being merely interesting and starts becoming something the seismological and heliophysical communities will need to address directly. Until then, the Calama earthquake stands on its own. A magnitude 6.9 in the Nazca Slab, 109 kilometers below the Atacama Desert, on the same trench that produced the largest earthquake ever recorded, at the bend in that trench where stress concentrates and the slab kinks. A reminder that the most destructive seismic events on this planet do not always look the way the headline number suggests. And, in the same minute, a coronal mass ejection from a part of the sun that should have been out of the forecast. The aftershock window is open. The proton storm is decaying. We will be tracking both as they develop.